Hello, my name is Cesar. I am coming from Brazil and I am going to present my work entitled Improving Supervised Superpixel-Based Codebook Representations by Local Convolutional Features. As we all know, deep learning techniques are the state of the art in the ImageNet competition, but they require large amounts of annotated data to be trained. And normally it is difficult to annotate the data because it is an error-prone and time-consuming task. In this sense, the visual words, also known as codebook representations, are a technique that perform well with small training sets, and as such they have the potential to overcome the absence of annotated data. Also, they succeeded in the ImageNet competition before deep learning. Nevertheless, they mostly don't use the image category because they build a single dictionary, and also they extract interest points from each image, which gives no correspondence between those points. So in this sense, our proposal is to use class-specific superpixel segmentation to detect the interest points, build dictionaries that are specialized for each class, and use random weight and convolutional features to build the local feature vectors. A brief introduction to codebook representations. They have the goal of finding the visual dictionary, which is basically a set of visual words that represents the images as histograms of those visual words. And in this case, for each image, it encodes a set of local feature vectors as one global feature vector for each image, as I said. And its pipeline is divided in 4 tasks. The first 2 are the interest point detection and local feature extractions, which have the goal of extracting the most relevant points and characterize them as feature vectors. And the most used methods are sift and surf. The second part is the visual dictionary construction, which has the goal of finding the visual words, and it is done by performing a clustering process using the local feature vectors, and the visual words are defined as the centroids of those clusters. In this case, the most common method is k-means. And finally, the global feature vectors encoding task is performed by building the global feature vectors for all the images, and they are basically defined as the histograms of the visual words. In this sense, our proposal is divided in 3 parts. The first one is to perform interest point detection using class-specific superpixel segmentation. And for this, we create an stacked image with all the images from each class, and then we apply the technique called iterative spanning forest to perform superpixel segmentation. And with this, we are creating a coordinate space which is common to all the images in the class. And then when the detected points are related to each class and to the object borders, which is important for this technique. In a few words, the iterative spanning forest technique represents the image as a graph in the image domain. It computes a spanning forest from that graph, which is rooted at some estimated seeds, and then the superpixels are defined as the spanning trees rooted in those seed pixels. The second part is the computation of the local feature vector by using random weight convolutional features. CNNs traditionally define an architecture, normally using pre-trained weights, and then perform feed-forward and backpropagation processes and repeat this during several epochs. But the drawbacks of this is that they have to optimize millions of parameters, and also supervised CNNs require large training sets. For this, the first part of this proposal is to use random weight CNN without backpropagation. For this, we define kernels that have normalized and centralized weights with no bias, which is basically a texture structure. And we define the feature vectors by performing a single feed-forward pass plus a flattening process. But one problem with this approach is that it produces very large feature vectors because of the flattened images. And so the question is how to maintain good accuracy with less features. For this, the second part of this proposal proposes to encode these convolutional features with a technique called BIC, which is basically a simple and fast color and texture descriptor, which first quantizes the image, this is simplifies the color information, and then analyzes the four neighbors to detect border and interior pixels, and finally computes separated histograms for border and interior pixels. Then the idea is to apply this descriptor to every filtered image that was produced by the CNN. And finally, the feature vector for each image is built by concatenating these big histograms of all the filtered images. And finally, the visual dictionary learning process is done by using the optimum path forest technique, which basically is a clustering algorithm, which defines the feature vectors as a graph, but in this case in the feature space domain, and it also computes a spanning forest for some defined routes, and the clusters are defined as the spanning forests. And the visual dictionary definition is performed by using the roots in the forest, which are basically the centroids, and they are the visual words. And we apply this process for each class, so we are building one dictionary for each class. Talking about experiments, the context of evaluation is the classification of intestinal parasite images, which is a problem in where we have a large amounts of unlabeled data sets. The annotation requires trained specialists. And the problem of interest is the classification of the 14 most common species of parasites in Brazil, which were divided in two data sets. As we can see in the images, we have a high similarity among classes, the figures A and B, and also high similarity with fecal impurities, which is the case of figures A and C. In the case of the data set, they were split in three subsets. We use 1% for feature learning, which is called ZFL, which is basically the Bajo Visual Words pipeline. 49.5% for classified learning, which is called ZCL, and the remaining for classified evaluation, which is called ZE. And the performance metrics used were accuracy and kappa measure. I would like to highlight the fact that we are using only 1% for feature learning. Well, the first part is the analysis of the interest point detection and dictionary estimation methods. And in this case, we are evaluating the impact of category information. For this, for the case of dictionary learning, we are comparing OPF versus OPF per class, and in the case of interest point detection, we are comparing grid sampling versus ISF per class. For both cases, we can see that we had an improvement in the kappa measure. So this is an indication that category information is important for this problem. And then, talking about the architecture of the CNNs that were used for local feature vectors extraction, we use different architecture with random weights, and then we apply a flattening process on the filtered images. For this, we used networks with 1, 2, and 3 layers, and also the AlexNet, which is a more known network which uses 5 layers. And also we tested different stride values. The results showed that the base approach was the one that used more layers and lower stride. Also, we observed that they produced a similar number of visual words, but very different number of features. And this is basically because of the number of kernels on each layer, basically in the final layer of each network. So in this part we used the big descriptor, as we explained before, to encode the feature vectors, and this dramatically reduces the number of features, in this case 5 times less features, while maintaining high accuracy. And finally, talking about the comparison with CNNs and other Bajo Visual Word methods, we used 3 baselines, which are variants of the AlexNet network. The first one is the FT, which used pre-trained weights. The second one is FF, which used also pre-trained weights plus frozen feature extraction layers. And the last one was RW, which used random weights plus optimization. All of them used fine-tuning using the ZFL and ZCL training subsets. And on the other hand, for the case of the Bajo Visual Words baselines, we used for the two variants grid sampling and the big descriptor and soft assignment, and one of them used OPF for clustering, and the other K-means to detect the visual words. In the results, as we can see in these graphs, we obtained better results than the other Bajo Visual Words approach, which are the lines in those plots. And also we obtained much better results than AlexNet with random weights. In one specific case, we obtained 60% more, which is a huge advantage. And also we obtained comparable results to AlexNet with fixed feeds, with frozen feeds. It's important to highlight that it was trained using millions of images from the ImageNet, while we only used 1% of the dataset. So it is a very important result. Well, that would be all. Thank you very much.